This is B.Naresh, working as assistant professor in a EC department. Today we are going to discuss MOSFET construction and its characteristics in depletion mode. So before going to this construction and the characteristics, first I need to recall what is a FET, where the FET is defined as where the FET is defined as field effect transistor. And generally, we know that we have the two types of the transistor. One is represented as bipolar junction transistor. Another one is represented as field effect transistor. In a bipolar junction transistor, the conduction depends upon both the charge carriers, that is, majority charge carriers as well as the minority charge carriers. So hence, and that particular transistor is called as the bipolar junction transistor. And coming to the field effect transistor, in a field effect transistor, the conduction depends upon only the majority charge carriers based on the construction. Either while constructing any field effect transistor, we can choose either a N-type materials or a P-type materials. So based on the utilization of the materials while constructing the field effect transistor, and it has the majority charge carrier, that is either a electrons or a holes. If we are using the N-type material, we know that the majority charge carriers are electrons, and if we are using a P-type field effect transistor, then we know that the majority charge carriers are holes. So hence, so that is the reason here it is represented as a FET is a device in which the flow of current through the conducting region. So again, it is represented as, why it is called represented as a field effect transistor means, when either whatever the FET, we are going to control the current, that is a drain current. It is represented as ID. A drain current is controlled by an applied electric field. Hence, this type of the transistor is called as the field effect transistor. And from this representation, the drain current is controlled by an applied the electric field between the two terminals, means in between gate and the source, as well as drain and the source. So we need to apply a biasing voltage between gate and the source as well as drain and the source, and based on this amount of applied electric field between these two parameters, then it can be controlled the flow of current across the transistor. Hence, that particular device is called as the field effect transistor. And based on that, here, so just now we discussed that. So the current conduction is only that depends upon the majority charge carriers. Based on this representation, we can say that the field effect transistor acts as a unipolar device. Why it is a unipolar means, it depends upon only the majority charge carriers. So based on that, either it considers the electrons or it depends upon the holes. Hence, it is also called as a unipolar device. And based on that, we know that the FET is classified as two types. One is represented as junction field effect transistor. It is also represented as JFET. Junction field effect transistor is also represented as JFET. Another one is a MOSFET. It is called as, where M indication is metal, O is oxide, S is a semiconductor, and the field effect transistor means metal, oxide, semiconductor, field effect transistor. It is represented as MOSFET, MOSFET. And it is also called as insulated gate field effect transistor. And here, so again, either in a JFET or a MOSFET, based on the construction, again, it is classified into two types. One is represented as N type or N channel JFET. Another one is either P type or a P channel JFET. Similarly, this MOSFET, it is also classified as the two types. One is enhancement, another one is depletion type. So in enhancement, again it is classified into either based on the construction, either it is N type or a P type. In a depletion also, it is considered as N type as well as the P type. So these are the classifications based on the constructing of either a junction field effect transistor or a metal oxide semiconductor field effect transistor. Now we'll see in the last sessions we observed that how we constructed the JFET as well as how we constructed the a MOSFET in a enhanced mode, and we also observed the characteristics of MOSFET in a enhancement mode. Now we are going to discuss the construction of a MOSFET in a depletion mode. So we have the two types. So means one is enhancement, another one is depletion. In both the cases, the constructing of the MOSFET is the same, but the difference is in an enhancement, while constructing, is not created any channel between the source and the drain. But coming to the depletion type of MOSFET, while constructing the MOSFET, it creates the channel or it establishes the channel between the source and the drain. So why the channel is required means we need to allow the charge carriers from the source to drain. Hence, it allows the maximum flow of the current across the drain or drain to source. Hence, so we need to establish or we need to create a channel between the source and the drain with an applied electric field between the gate and the source as well as the drain and the source. So the construction part is the same, but just you remember the difference between enhancement and the depletion mode. In an enhancement mode, in a construction, there is no channel, but in a depletion itself in the construction, it contains a channel between the source and drain. And we know that again, so the depletion mode or enhanced mode, we have again the two types based on the construction. We have the N channel as well as the a P channel. So we are going to define either it is a N channel or a P channel depletion type of MOSFET. So hence I represented these are the two forms, enhancement and as well as depletion type. So here there is no channel and the channel is established while constructing the MOSFET. Now coming to this construction, how we are going to construct the MOSFET either in a enhancement or depletion mode. But now we are going to discuss how we are going to construct the depletion mode of MOSFET. If you observe this MOSFET, we have some terminology. So where the FET indication means the field effect transistor, and the way M means metal, O means oxide, and S means semiconductor. And if you observe these terminology, we have the two conducting materials. One is a metal, another one is a semiconductor. Metal as well as the semiconductor, these two are acts as a conducting materials. Now we need to construct, we need to approach from the bottom to top approach. while constructing the MOSFET. Means we need to start from the semiconductor. So hence, so here in this construction, we have the two types of the MOSFETs under this depletion mode. So that is, we know that one is a N type, or it is also called as N channel depletion type MOSFET, or, and another one is, it is called as a P type or a P channel enhanced depletion mode of the MOSFET. And you remember in principle, while constructing the any MOSFET, either in an enhancement mode or a depletion mode, if you want to construct this N type, the substrate should be opposite material. The substrate should be opposite material. Means if you want to construct this N channel depletion type, we need to take the P type substrate. If you want to construct this P type or a P channel depletion type MOSFET, we need to choose a N type substrate. So hence, suppose I'm going to construct this N channel. So I'm going to take a substrate is a P type substrate. First you consider this P type substrate, and this is called as a P type substrate, and it is also acts as a semiconductor. Then after this, we need to diffuse, and we know that again, either any FET, JFET or a MOSFET, we have the three terminals. One is represented as gate, another terminal is represented drain, another one is source. Hence, we need to diffuse a heavily doped N-type material at the top of these corners, and this is represented as N plus, and this is also represented as N plus, where the N plus indication is for the doping levels are very high compared with the normal extrinsic semiconductor. So hence it is represented as N plus. And we are diffusing the two materials at the top of opposite ends. And for this, we are connecting some electrodes. One electrode is represented as source. Another electrode is represented as drain. So hence, we place this semiconductor now. So if you observe this one, metal and a semiconductor, those two are the conducting materials. Hence, if you want to separate between this metal and another conducting material, we need to place a dielectric media between these two conducting plates. Hence, now we are going to insert a dielectric media that is acts as a insulator, and it is represented as a silicon dioxide, SiO2. And here, this silicon dioxide acts as a insulating media. So this is semiconductor or a substrate. Then we place the oxide that is represented as silicon dioxide. Then the last one is the top one is a metal. So hence we are going to place a metal, and this is a metal conducting material. And for this metal, we place the one electrode. That electrode is represented as gate. So hence, this is M, metal, oxide, and this is semiconductor. Hence, this type of the construction is called as MOSFET. But in an enhancement, but there is no channel is created between the source and the drain while constructing. But in the depletion type MOSFET, we need to establish a channel between the source and the drain ends, and this is called as the channel. So here it is represented as channel, and this channel is represented as N-type material, N channel. Hence, this type of the construction belongs to a N-channel depletion type MOSFET. Similarly, if you want to construct a P-channel or a P-type depletion type MOSFET, so first we need to take a substrate. So if we want to construct the P-type means, then we need to take the opposite material, and that opposite material is represented as N-type substrate. Then we need to diffuse a heavily doped P-type materials, opposite ends. Then for this, we need to connect the electrodes. One electrode is represented as source, one electrode is represented as drain. Then we need to place a dielectric media. It is represented as silicon dioxide. So here the silicon dioxide acts as an insulating media. Then at the top of this insulating media, we need to place a metal conducting plate, and this metal is connected to one electrode that is called as gate. Now we need to establish this channel, and here this channel is represented as a P-type channel. Hence, this type of the construction belongs to a P-type or a P-channel depletion type MOSFET. And similarly here it is called as a N-type or a N-channel MOSFET under the depletion mode. So this is the construction part, how we are constructing a depletion type of MOSFET. Now we need to identify the behavior of the MOSFET under this depletion mode. We need to verify the functionality of the MOSFET. So if you want to verify the functionality of any semiconductor devices, we need to apply a external force. So that external force in terms of a voltage or electric field. So hence, now we are going to analyze and what type of force is required to allow a conduction across the field effect transistor. And based on the construction and the representation of the field effect transistor, and we know that we have the three types of the terminals, and where it is represented as gate, drain, and source. Out of these three terminals, the source itself, it acts as it acts as the input of the field, means it gives the charge carriers to allow the drain current in a field effect transistor. Hence, we need to apply a biasing voltage between source as well as, so whatever the charge carriers are emitted from the source, all those charge carriers to be reached to the drain, then only it allows the flow of conduction across the field effect transistor. So that is the reason we need to apply a biasing voltage between the source and drain, and across these terminals, in between these two terminals, we need to identify how much a potential difference will be absorbed when we are applying the biasing between or a electric field between the source and the drain. And that is represented as a VDS, drain to source voltage. Now coming to you, and which type of electric field, means what type of electric field is required to allow or to repel the charge carriers from the source to drain. If you consider the N-channel depletion type MOSFET, and in this N-channel depletion type MOSFET, source is made up with the N-type material. And we know that if it is an N-type material, the majority charge carriers are electrons. and electrons are a negative charged particle. Hence, if you want to repel this electron from this place to another place or source to drain, we need to apply some force to repel the discharge carrier from the source to drain. Hence, so which type of energy is required to repel the charge carriers from the source to drain? And based on the majority charge carriers of the source, here we need to apply the source is biased with the negative pole of the battery. Hence, the source is biased with a negative pole of the battery, and with respect to, so means we know that the electrons are always attract the positive pole of the battery. So hence we need to create the whatever the charge carriers or repel from the source all to be reached towards the drain, means that the drain is biased with a positive pole of the battery. So hence a negative pole of the battery is connected with the source, and a positive pole of the battery is connected with the drain terminal. And this type of the biasing voltage here it is represented as V. And due to an applied electric field between the source and the drain, due to this force, negative force, and based on this n-type source material, the majority charge carrier, that is electrons, are repelling from the source to drain to allow the flow of current. Then, now we need to control the flow of conduction. So here there is no controlling. If you are increasing the biasing voltage between the source and the drain, the maximum flow of current takes place across the field effect transistor. Now we need to control the flow of drain current in this depletion type of MOSFET. Hence, again, another biasing is required to control the flow of drain current or to limit the flow of drain current. For this case, we require a biasing voltage is required between gate. And again, so which type of biasing is required for this case? Means the gate is biased with the positive or a negative. So when in this point, when a gate is not biased with any type of electric field, it does not affect this gate is does not affect the channel. Now our aim to be, we need to reduce the channel width or area to limit the flow of charge carriers from the source to drain. Hence, let us consider we have the two conducting plates based on the MOSFET construction. So here this is represented as metal, oxide, and a semiconductor. If you recall the capacitor principle, and we know that the capacitor is also contains two conducting plates, and in between these two conducting plates a one dielectric media is exist. So hence, so if you observe this construction also, this is the metal is a conducting plate, and this is the insulating media, that is the silicon dioxide, and this is another semiconductor. Hence, in between the two conducting plates we have one insulating media, hence it also acts as a capacitor. And we know that for the capacitor, if you apply the positive pole energy, then so at the end of the another this plate, it produces a negative energy. Then so again this is positive. So at the second plate again will produce the negative. Suppose if you apply a forward biasing voltage between this gate, so what happens here? So here it generates a positive. If suppose let us assume that if we are applying the positive, then so it is negative. Then again it is positive. Then here it generates the negative. So negative means it generates a negative energy across the channel. If you are producing the more negative energy in a channel, what happens? Electrons again repelling more fast compared with the previous energy. Hence, the conduction rate is also again increases, and there is no limits, or there is no limit to flow of the current in this device. Hence, the gate should be, we need to, if you want to control the flow of charge carriers from this source to drain, now the gate is biased with the negative. So means, so again this is the conducting plates. If the gate is biased with a negative, means if you apply the negative energy here, this is positive and this is negative and this is positive. Means, so if you apply the negative here, now this becomes positive and this negative, and here this is becomes positive. Means, positive means a positive energy is established in the channel. Means it acts as a immobile ions. Means it completely occupies the some area or a width of the channel. So hence the area of the width, the area of the this channel will be reduces. Hence it limits the flow of current. So that is the reason the gate should be biased with the negative energy with respect to the source. So gate is biased with the negative pole with respect to the source, means source is connected with the pole. And this type of the biasing is called as the VTG. So these are the two biasing voltages, means to control the drain current. So initially we discussed that the FET is called as the field effect transistor. Why? Because of the drain current is controlled by an applied electric field. So here also the drain current is controlled by an applied electric field between gate and the source, as well as the drain and the source. So hence it allows the some amount of the maximum current, or it limits the flow of current. Suppose similarly, if you want to make the biasing for a P type, let us consider if it is source is here. In this case, in a P channel MOSFET, let us consider the source is made up with P type. So if it is a P type, we know that the majority charge carriers are holes, and holes are positive charge particle. So hence we need to apply a positive energy to repel or to break down the covalent structure between this source material. Hence the source is biased with the positive pole of the battery with respect to the drain. Why? Because of that, the holes are attracting the negative pole of the battery. So our aim to be whatever the charge carriers are repelled or emitted from the source, all the charge carriers to be reached at the drain to allow the flow of current in a field effect transistor. Hence, based on the construction and based on the utilization of the materials, we need to apply the biasing. So if it is a P type or a P channel, so based on the principle, source is biased with the positive pole of the battery with respect to the drain. Hence, a negative pole is connected to drain. So similarly, so here the gate is biased with positive. So why? Because of the this is a P type, means the holes are the majority charge carrier. So for this case, we need to disappear. So means if whatever the charge carriers are emitted, those charge carriers are not reached to the drain, means it does not allow the flow of current. So if you are creating the negative energy, whatever the charge carriers are emitted, that should be paired with this energy, but it's not reached to the drain side. Similarly here also, if you are creating a positive energy in the channel, electron is a negative charge particularly. So whatever the charge carriers are emitted, that should be paired with this positive energy. Hence, is not reached to the drain. Hence, the movement of the flow of charge carriers concentrate is a decreases. Hence, the drain current is also decreases. So that is the reason. At this point, the gate is biased with the positive with respect to the source. So this is the complete analysis of the construction of the MOSFET in a depletion mode, either in a N type or a P type. After the construction, if you want to identify the behavior or the characteristics of that particular transistor, we need to apply a external field or electric field. So based on that, I shown this is what we discussed now for an N channel. So if it is an N channel, this is represented as P-type substrate, and we are defining the two materials that is represented as heavily doped material. One is connected to source, one is connected to drain, and this is a metal, conducting metal. So then gate is a biased with a negative, hence it is a represented VGG, and the source is also connected to the negative pole. With respect to drain, it is a represented as VDD. So these are the symbolic representations of the MOSFET in a depletion type. So this is for N channel and this is for P channel. We know the three terminals, drain, source, and this is also called as the body or substrate. Body or a substrate. Here also this is body, or B is indication for body or a substrate. So gate, and this is silicon dioxide on one metal, and this is drain and the source is semiconductor. Metal oxide semiconductor. Here also this is metal oxide semiconductor. Metal oxide semiconductor field effect transistor. Now we'll see that a construction. Now we are going to observe the characteristics. So based on this construction, now we need to verify the behavior of the MOSFET under this depletion mode. And generally, we know that the two types of the characteristics. One is represented as drain characteristics. It is also called as output characteristics. And another one is transfer characteristics. And from these two characteristics, we need to learn how this drain current is controlled by an applied electric field between the gate and the source, as well as the drain and the source. To analyze or to understand this, the functionality of this MOSFET, and from that representation, the field effect transistor, the drain current is a functioning with respect to the biasing voltage between drain and a source, as well as gate and a source. VDS means the biasing voltage is between drain and the source, and similarly the biasing voltage between gate and the source. If you want to identify or if you want to draw this output characteristics, we need to plot this output characteristics to be plotted in between the drain current versus drain to source voltage by making the gate to source voltage is constant. We need to plot the characteristics or plot the between drain current versus drain to source voltage by making gate to source voltage is constant. Similarly, if you want to plot this transfer characteristics, the transfer characteristics are drawn in between the drain current versus gate to source voltage by making the drain to source voltage is constant. So these are the principles to identify the two types of the characteristics, either the drain characteristics or a transfer characteristics. Now we'll see in detail for a drain as well as the transfer characteristics. So if you want to identify this, if you want to plot the drain characteristic, so just now we discussed that the drain characteristics are output characteristics are drawn in between VDS and ID. Hence, the x-axis is taken as VDS, y-axis is taken as drain current by making gate to source voltage is constant. To understand this operation, so here I am going to take the construction. I am going to for this is for N channel characteristics, N channel depletion type mode characteristics. And just now we discussed this. If it is N channel, we need to take a P-type substrate or a P-type body, and these are N plus. Now this is the channel, and this is for source, drain. Now I'm going to place some insulating media, SiO2. At the top, I'm going to place a metal, it is gate. So otherwise, if you're taking a symbolic representation, this is gate, drain, and a source. This is the choice, body. So now we need to apply the biasing between drain and the source. Drain is connected to positive pole of the battery with respect to the source, and the gate is connected with the negative pole with respect to the source. It is called as the VGG, and this is VD. Then we need to measure a potential difference between drain and the source, is represented as VDS. A drain current is a flows, that is represented as ID. And similarly, here we need to measure a potential difference between gate and a source, is represented as VGS. Now, let us consider in a first case when VGS is 0. If I am assuming that VGS is 0 and VDS is also 0. So let us consider the first case when a VGS is a 0 and VDS is a 0. Means here I am not applying any biasing voltage between the gate to source terminals as well as drain to source terminal. Means there is no external force, means there is no repelling of the charge carriers from the source to drain. Hence, it does not allow any flow of conduction in this field effect transistor. Hence, the drain current is represented as 0. And the second case, just when VDS is just increased from the 0, VDS is increased from the 0, and again VGS is 0. When a VDS is, or otherwise let us take when VDS is maximum, 0 to maximum, but VGS is 0, means when VGS is 0 means, and this source is replaced with, so means VGG is replaced with a short circuit. The voltage across the gate and the source is represented as 0, means it is represented as short circuit. Now we are varying this biasing voltage from 0 to maximum when VGS is 0. When a VGS is 0, means if you're not applying any electric field between the gate and the source, what happens? It does not affect this potential energy on the channel. This is the channel, and this is the maximum area is created while constructing this MOSFET. Hence, due to this applied force, how much energy we apply, based on the amount of energy, it repels the number of charge carriers from the source to drain. Hence, the charge carriers are repelling from source to drain. Hence, the maximum drain current is flowed from the drain to source. Hence, it allows the maximum drain current when, why? Because of that, this we are applying the gate voltage is 0, means this energy is not affect the channel parameters. So hence, so that is the reason it allows the maximum current. So when I reach the maximum current, it becomes saturated, then means it becomes a constant. Let us take this is VGS is equal to 0. Now for the same condition, the third condition I'm taking, when VDS is again increasing from 0 to maximum, but VGS is decreased from the 0. Why it is a decrease from 0 means, to control the flow of drain current, we need to apply a negative energy across the gate terminal. So that is nothing but VGS is decreased from 0, or we can apply a small negative voltage. Suppose I'm applying the minus 1 volt across the gate to source. Hence, Now we need to apply a negative voltage, means gate is a biased with negative pole of the battery with respect to the source. Now I consider this VGG or VGS is equal to minus 1 volt. So hence, now what happens if I apply the negative voltage, then the source is again biased with so now if you apply a negative voltage, so it creates a small amount of positive electrodes in this region. So this is maximum area previously, but now due to this applying of a negative voltage across the gate, it creates some positive electrodes in the channel. Now what happens? It reduces this width of the channel. So that is the reason. The flow rate is also decreases. Hence, the drain current is decreases. So means, so if you want to allow the maximum current, it requires a more time period compared with when VGS is a 0. Hence, when a VGS is decreased from 0, drain current is also decreased. Why? Because of that. So it reduces the channel area. So that is a reason. So that is the reason. If channel area is reduces, means R is equal to rho L by A. Area is reduces, means R is increases. If R is increases, I is decreases. We know that I is equal to V by R. But what we have done, when the gate voltage is reducing from the 0, what happens here? Area is decrease. The channel area is decreases. If the channel area is decreases, the resistivity of the channel is increases. If the resistivity of the channel is increases, the current is decreases. So hence, so when VGS is decreased from the 0, so which current is reduces? The drain current is reduces. Why the drain current is reduces? It reduces the area of the channel. Hence, it increases the resistivity of the channel. That is the reason it reduces the flow of drain current from the drain to source. Hence, here I drawn the curve should be below of this line. Let us take this is when VGS is equal to some minus 1 volt. So similarly, when goes on reducing this VGS, let us take suppose this is I taking the minus 5 volts. So means here I apply the more negative voltage across the gate terminal. Now what happens? It creates the more positive electrodes on the channel. So whenever it creates a more positive channel, again area is again further reduces. Area is again further reduces, means if area is a further reduces, the resistivity is more increases. If a resistivity is a more increases, the current is more decreases. So that is the reason. Always when you are decreasing the VGS from the 0, always the drain current is reduces. Hence like this. When VGS is equal to minus 2 volts, when VGS is equal to minus 3 volts. Let us take at very large reverse voltage. Let us consider at very large reverse voltage. Let us assume that due to the very large reverse voltage is passing through the gate terminal. Let us consider means due to that large voltage, it completely occupies the channel area. It completely occupies the channel area, means that here this area becomes 0. Area becomes 0, means it completely dimensions the area of the channel due to the applied a large reverse voltage between the gate and the source. Due to this, whenever area is a disappear, means R mean comes infinite. If resistivity becomes infinite, the current becomes 0. Hence, at very large reverse voltage, the drain current becomes 0. So this is ID is 0 at VGS is a large reverse voltage. So this region here it is called as a pinch of region. So these are the characteristics or a drain characteristics. So hence I shown based on all these analyses, based on all these conditions, here I drawn this the characteristics of the drain. So in types, in this case, x-axis represents VDS. Just what we discussed, the same I represent in the graphically. VGS is a 0. VGS is decreased from the 0 means what happens here? Drain current is decreased. Now we need to identify some regions in this characteristics. We have the regions. One region is called as linear region. Another region, we have the saturation region. And another point, it is also called as a pinch of voltage. It is called as the pinch of voltage. And what is a linear region means? It in this region, it satisfies the ohmic characteristics. It satisfies the ohmic characteristics means V is increases, I is also increases. That is the reason. This type of the region is called as the linear region or the ohmic means. At which point or at which voltage the drain current becomes maximum and below of that region is called as the linear region. At which point the drain current becomes maximum and below of that region is called as linear region. And again, at which region or at which point the drain current is a maximum or a saturated or it becomes a constant, then that particular region is called as the saturation region. At that point, the particular voltage is represented as the pinch of voltage. So these are three important characteristic regions from the drain characteristics. One is the linear region, pinch of voltage, and saturation region. So the same points I represented here. Now coming to the transfer characteristics, another characteristics are transfer characteristic. If you want to plot this transfer characteristics, we need to plot the characteristics between drain current versus VGS by making VDS is constant. So if you observe the previous circuit in that, so means I'm going to plot, and here again the VGS is in this N-channel depletion type MOSFET. We are applying the negative biasing voltage between the gate and the source. Hence, the x-axis I taken as a negative quadrant that I considered as VGS. And the y-axis I taken as drain current. It is represented as ID. So in this case, so again this is the same biasing circuit. We need to use the same circuit. So for this case, now we need to maintain a constant biasing voltage between the drain and so means we need to make this VDD is a constant, that becomes VDS is a constant. By making this VDS is a constant, then we need to vary this gate voltage. Now we need to observe how the drain current is controlled. Hence, so from that should be we observed from these characteristics. Let us consider, and I apply a constant force across the source. When I apply a constant force across the source to drain, now VGS is decreased. So let us take when VGS is 0, what happens here? Drain current is maximum. When VGS is reduced from the 0, drain current is decreasing from the maximum to some point. Again, it goes on reducing this VGS voltage, drain current is also reduces. Hence, to plot this transfer characteristics and what we observed, so in the from these characteristics, when VGS is a 0, out of all these parameters, when a VGS is 0, the drain current is maximum. Hence, here I am going to represent, and this is when VGS is a 0, the drain current is a maximum. This is the maximum, and this is here also called as a drain to source saturation current, IDSS. It is called as drain to source saturation current. Means that saturation current is nothing but it allows the maximum. It becomes a constant. If your VGS is decreased from the 0 from these characteristics, if a VGS is a decrease from 0, what we observe, drain current is also decreases. Hence, when a VGS is decreased from 0, drain current is also decreases. At very large reverse voltage, we observe that where So in a previous case, at very large reverse voltage, what we observed, the drain current completely becomes zero. Why? Because of that. At very large reverse voltage, it completely dimensions the area of the channel. Hence, the drain current becomes the zero. So based on that representation, at very large reverse voltage, drain current becomes zero. At this point, this region is called as VP, is nothing but a pinch of voltage, or it is also called as a pinch of state. It is also called as a pinch of state or a pinch of voltage, VP. And that VP is also called as VGS off. Means that VGS off means is enters into the non-conducting state. Why? Because of that, the drain current is represented as zero. So hence, from that I drawn this is a transfer characteristic. So up to this point, so today we observed that the construction of the MOSFET in a depletion type, as well as we discussed the characteristics of the MOSFET in a depletion mode. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.